Hi, in this video, I'm going to walk through the solution of the classical damped and forced harmonic oscillator problem. I'm going to follow the treatment in this great little book, big book. It's about 700 pages, and it contains most of the tricks you'd ever want to know in a graduate physics course. Example subjects. Got classical vector spaces, calculus of variations, vectors and matrices, vector spaces, Hilbert spaces, complex variable theory, Green's functions, integral equations, Hilbert space integral equations, and group theory. If there's this book is intended as a one-stop course for everything mathematical that you'd ever want to need to know in graduate physics, and it's quite comprehensive. You can find a lot of good tricks in there. In about 4 pages of very dense mathematics, they cover the Green's function solution to the harmonic oscillator problem with a damping term and a forcing function. So if we were to write the classical harmonic oscillator is just x double prime plus omega naught 0 squared x equals 0. There's the unforced homogeneous classical harmonic oscillator problem. So we add some complexity here by adding in a forcing term, a damping term, and adding in a forcing function. You've probably had in your differential equations course, you've probably had to solve problems like the harmonic oscillator with a cosine of omega prime, say, t. Something like that. That wouldn't be an unreasonable problem to have in a differential equations course. But how do you go about solving this in a more general sense? And that's what we're going to do here. I'm not sure how long this video series will be, because I don't think I can get through it all in one video. So let's see how we go. So first thing we have to do is we have to come up with a solution for the homogeneous problem. And so that is, I'm going to write it out. So our equation is x double prime plus 2 gamma x prime plus x equals 0. And we'll use our usual trick, assuming that x equals maybe some constant times e to the st. And if we go and plug this in, then we get a times s squared plus 2 gamma s plus 1 equals 0. Did I get that all right? So take the derivative of x, we bring down an s, so we have as e to the st. Okay, that's good. And so we have a characteristic equation which must equal to 0. So if we go and solve this, let's see, we have s plus gamma squared minus gamma squared plus 1. Oh, I see what's wrong here. I missed my omega naught squared. Omega naught squared. Omega naught squared equals 0. So we have s plus gamma squared equals gamma squared minus omega naught squared, or s equals minus gamma plus or minus the square root of gamma squared minus omega naught squared to the 1/2. So if we plug this back in, we have x equals a e to the st, which is e to the minus gamma t times e to the plus or minus, let's say, plus or minus, let's factor out an I here, omega naught squared minus gamma squared to the 1/2. So if our damping term gamma is 0, then we have a minus in the square root, and so we'll assume that we have gamma is a perturbation around the intrinsic angular frequency omega naught, and so we have as two solutions we have some constant a1 e to the minus gamma t cos. That's a messy cos. Let's try again. Only slightly better. Cos of omega naught squared minus gamma squared t, and we have another solution times the sine omega naught squared minus gamma squared t. There's two linearly independent solutions to the homogeneous problem, and we'll use those a bit later. Now we're going to move on to the general solution. And for the general solution, we're going to use a Fourier transform. And I've written out the form of the Fourier transform that's used in this book and used in most physics, which we have a symmetric solution of the Fourier transform function. It's 1 over the square root of 2 pi, so it's e to the minus kt f of t dt. If we want to do the inverse transform, then that's as simple as 1 over root 2 pi, same range, but we flip our sign, e to the minus kt f hat k dk. And there's lots and lots of ways of writing Fourier transforms. You can have a 1 over 2 pi in the front and nothing in the inverse transformation, or the other way around. You can have lots of different selections for what your transform variables are going to be. This is the form that we'll be using. Just moving those out of the way, let us go and plug that in. What we want to do is we want to Fourier transform our whole differential equation. So that's x double prime plus 2 gamma x prime plus omega naught squared. This time I didn't forget the omega naught squared. X equals f of t. And we Fourier transform all of this, which means we have 1 over root 2 pi e to the, and Fourier transform we're using plus ikt x double prime plus 2 gamma x prime plus, and now if I'm Fourier transforming omega naught squared x, that is just going to be omega naught squared times x hat of k, and if I'm Fourier transforming our forcing function, it will just be the Fourier transform of the forcing function. So we have to do something with our derivative terms in order to put them in terms of x hat of k. So let's do that. So if we start with what is the Fourier transform of the derivative? Let's write that out. And we can omit the 2 gamma term for just or temporarily. So what's happened if we have, that is a messy root, do minus infinity to minus infinity e to the I k t dx dt d. Yes, and I missed my dt earlier. Did I get it up here? I got my dt's and dk's up there. Okay. So here's a Fourier transform of just the derivative of x. What we can do is we can use integration by parts. So we can write this. All right, let's say we have, if we had d dt of e to the ikt, e to the ikt x, this is just as an aside, not as an equality, then what do we have? We have ik times e to the ikt x plus e to the ikt dx dt. So that's applying chain rule to this particular term, and now we can flip it and insert this expression in here. So plugging that in, we have 1 over root of 2 pi integral. So e to the ikt dx dt is dt of e to the ikx iktx minus ik e to the ikt t x x. And so we have the integral of the derivative. So we just have to evaluate this across the boundary. So that term becomes 1 over root 2 pi e to the I k t x between minus infinity and infinity. And we assume that x is Fourier transformable, so it vanishes on the boundaries of the integral. And we also have ik over root 2 pi of e to the ikt x dt. And there was a dt missing there. So this was the Fourier transform of x prime. We're left with 0. And so this is Fourier transform of x prime of t equals minus ik over root 2 pi of the Fourier transform of x valued at k. So there we go. There's one derivative. So we have a derivative. Each time we take a derivative, we see that we have a minus ik term that's pulled out. So we can similarly say that the Fourier transform of x double prime of t, assuming that the derivative of x prime of t vanishes on the boundaries of the integral, i.e. minus and plus infinity. What do we have left? We have minus ik squared, and there should not have been 1 over root 2 pi here anymore, because that is in the x prime of k. So we have just minus ik squared times x hat of k, which is minus k squared. Minus squared is plus 1, I squared is minus 1, we have minus k squared x hat of k. Now we can go and plug this all back in into our differential equation, and we're almost at a partway point for the Green's function that we want to evaluate. So remember that we had, so we will have here minus k squared times x hat plus minus ik times 2 gamma x hat plus omega naught squared x hat equals f hat. We have x hat, x hat, x hat. We can solve for x hat. And in terms of f hat, and what do we have left here? We have x hat of k. The Fourier transform of x is f hat divided by minus k squared minus ik gamma ik minus 2 ik gamma plus omega naught squared. Pretty cool. So, we now know that regardless of the form of the forcing function f, and for all non-zero gammas, well, zero gammas could be included too. We're going to omit them for reasons that become clear in a bit. So we're only going to consider the non-zero gammas for now. But we have a full solution for our variable, but we have to Fourier transform back in order to find the final form of our function in terms of t. So in terms of t, inverse transforming, we have 1 over the square root of 2 pi times the integral from minus infinity to infinity of f hat k e to the minus I kt dk over minus k squared minus 2 ik gamma plus omega naught squared. So this presumes that the denominator is non-zero. If the denominator was 0, we would get into trouble. So let's go and see under which conditions the denominator would be non-zero. And also, let us slightly tweak this and pull the sign out. So I'm going to make that minus, plus, plus, minus. So this just makes so if we want to look at what are the zeros of this function, where do they lie? And in particular, do they lie anywhere on the real axis? If they do, then we're in trouble. So let's make sure that's not the case. So what are the conditions for the denominator to be 0? That's k squared plus 2i k gamma minus omega naught squared equals 0. So that's going to be true when k plus I gamma squared minus I gamma squared minus omega naught squared equals 0, or k plus I gamma equals, and so let's flip this to the other side, so we have omega naught squared, and we have I squared, which is minus 1, times minus 1 is plus 1, but it comes to the other side, so we have minus gamma squared, and so k is, the denominator is 0 when k is minus I gamma plus or minus the square root of omega naught squared minus gamma squared. So provided that gamma is non-zero, these roots are always lying off the x-axis. So specifically, we have one at, so this is the imaginary axis and this is the real axis. Our roots are somewhere in the imaginary region distributed around. around the imaginary axis. So we have two roots, and we are evaluating our integral across the real axis from minus infinity to infinity. So we're perfectly within reason to put this in the denominator without worrying about division by 0. So now we want to see, how do we evaluate this? So having looked at these roots, we're going to go and write those as k1 equals minus I gamma plus omega naught squared minus gamma squared to the 1/2. And k2 is minus I gamma minus omega naught squared minus gamma squared to the 1/2. And I'd have to look in the book, but it could be that the sign choices that I've made differ from the sign choices in the book for their k1 and k2. It won't matter at the end because we're going to get rid of those. But what we will want to do is let us just plug those into our relationship here. So we have x of t is 1 over 2 pi minus the minus I kt f of k over k minus k1 times k minus k2. And this is the dk. Almost the form that we want this in. The thing that we still have to deal with is we have f of k here, where we actually are given f of t. So let's plug in our f of k, which is just the Fourier transform of f of t, and see what we get. So minus 1 over 2 pi. We have another 1 over 2 pi. We have an integral here of minus infinity to infinity, e to the minus I kt dk k minus k1 k minus k2 and f of k is a integral of e to the say minus t prime plus I kt prime f of t. So the Fourier transform of f of t, and we'll make that f of t prime, is going to be f of k. So now we have something that is self-contained in terms of f of t, evaluated at t prime. And what we can do is we can write this whole messy beast as a convolution. So this is x of t, which is 1 over 2 pi times minus infinity to infinity of e to the I k t prime minus t divided by k minus k1 k minus k2 k and f of t prime t prime. Now, we take this integrand plus our constant at the front. We call that g of t prime equals 1 over t pi e to the plus ik t prime minus t k minus k1 k minus k2 as a g of t and t prime. And so x of t and so x of t will be some constant times x1 of t plus another constant times x2 of t, where x1 and x2 are solutions to the homogeneous equation, which we found earlier, plus a convolution integral of our Green's function with f of t prime. So we convolve f, our forcing function, with our Green's function. This is Green's function in the sense that it's just a convolution integral, the integral kernel. We now have a full solution to the problem at hand, including the homogeneous terms that are just added in here. So our problem is now we want to figure out a closed form solution for our Green's function, which basically want to evaluate this integral in k-space along this real axis. And that is the problem for next time. So we've gotten as far as getting to we want to evaluate this as a contour integral, and we're going to have to refresh our minds of how to do a contour integral and come up with the end result for that contour integral. And once we do that, then we've essentially solved the full problem. This is basically two of the 4 pages of the solution from Byron and Fuller's treatment of this particular problem. And I think that is a good place to end for now.